Hello, this is Dr. Lori. Welcome back to our next video on arranging the data. So in our last video, we were introduced to a scenario where we have a hypothetical second study that was not actually done, looking at the relationship between DES and vaginal clear cell adenocarcinoma. And we imagined a situation where we have 20 cases and 40 controls. And of those 20 cases, 19 were exposed to DES, and out of the 40 controls, 3 were exposed to DES in utero. So I'd like to show you specifically how to set up what's called a 2x2 table. And the 2x2 table is amazing. The 2x2 table is very versatile and is used in many, many situations. And it is our primary tool when we start looking at data analysis for rare diseases. So here we go. One of the things that I like to point out right off the bat is that this top left corner is golden. This is where we are really looking at specifically what it is that we're trying to study. So we want to be sure that the cases who are exposed, this group right here, ends up in that top left corner. So what I'm going to do is this vertically, the columns are disease. And you could think of this as disease, yes, no. These are the cases. And these are the controls. And then on the row axis, this is our exposure. So this top row is exposed, and the bottom row is not exposed. So this is our risk factor. We could think of this as a risk factor, yes, no. And so notice that the yeses are in this top left corner. And I've done that specifically so that when I'm doing this repeatedly, I have a system and I always know how to interpret what I'm looking at. The other reason I like to do it systematically the same way each time is that this is specifically one of the ways that SPSS calculates things correctly. And so if we can get in the habit of doing the work correctly so we don't have to transpose or convert, then I think that can sometimes be helpful to our analysis. The next thing that I'd like to point out is that when we're doing a case control study, remember how we selected the individuals to be part of this based on whether they were cases or controls? What that means is that we started out by literally filling in the bottom boxes down here at the bottom. We have a total of 20 cases and we have a total of 40 controls. And so that really is our starting point. And then once we have collected our cases and controls, then we ask them, were you exposed or not? And what we found out up here at the top is that 19 of our 20 cases said, yes, I was exposed. Having a little pen issue here, sorry about that. I wanted to show up. 19 of our 20 cases. We also found out that 3 of our 40 said that, yeah, I was exposed. And so once you filled those 2 squares in, the rest of it, the not exposed, is kind of automatically decided because the exposed plus the not exposed has to add to 20 altogether. So this should be a number 1. 3 plus 37 is equal to 40. So now we have all of the cells in our table filled in, and I'm going to add one more piece of information over here on the right. This is not as important, but I'm doing it partially to be complete, and then also partially so that I can answer another question that comes up commonly for case control studies. So basically 19 plus 3 is 22. 37 plus 1 is 38. All of these should ultimately add up to the same total, right? 20 plus 40 is equal to 60. I sure hope that 22 plus 38 is equal to 60, and it is. So if I've done the math correctly, both directions should add to the same total. So this is my grand total. 60 is my grand total. Now, I'm going to do something that I call you absolutely would never do this. Okay? Absolutely not. But it's for the purpose of illustration. And that is, based on this table, can I calculate a prevalence of disease in the population? And the resounding answer to that question is no. No, do not ever do that. Prevalence is the number of cases divided by the total. Now remember, I said this was a rare disease, and so I had to collect all the cases I possibly could, and then I came up with some controls to compare it to, 40. But people mistakenly then say, oh, well, the prevalence is 20 out of 60. So, wow, a third of the population has vaginal clear cell adenocarcinoma. There's an outbreak. And that's absolutely wrong. You would never do this, okay? And this is actually one of the important disadvantages or limitations of a case control study, which is that we cannot calculate the prevalence of disease. I have forced there to be 20 and 40. That does not mean that 33% of my overall population out in the whole entire whatever state, city, county, whatever my baseline population is, that does not mean that 33% of my population has this particular disease. I have intentionally caused there to be that proportion in my study by manipulating the groups. One way that researchers say this is that we don't have true denominator data. In other words, my total, that thing that I divided 20 divided by 60, that is not representative of the population. So I don't have denominator data. I manipulated my groups to be this size. If I had only collected 20 controls, would that suddenly mean that now my prevalence of disease in the population has gone up to 50% from 33? No, it's because I decided how many cases I wanted, and then I collected a specific set number of controls based on my study protocol, and I cannot determine prevalence. This is the kind of thing that CPH exam questions are made of. They'll give you some kind of scenario like this and say, what's the prevalence? And one of the possible choices is you can't calculate it. So keep that in mind, because we want to make sure that we're giving accurate information. Sure, I can punch numbers into a calculator and give you the answer, but I have to understand the study design in order to know if those numbers mean anything. So just be really super careful about what numbers we punch into the calculator and expect to get something back. The other thing that I want to point out, and that is the kind of variable that we're using. Notice here that I have a yes-no variable. Disease is yes-no. I have cases and I have controls. If disease is yes, it's a case. If disease is no, it's a control. Same thing over here. I have my risk factor. If my risk factor is yes, then that person was exposed. If my risk factor is no, that person was not exposed. And reach back into your memory bank. If you have two possible choices for a variable, that's called a dichotomous variable. And so when we get to the place where we're entering variables into the computer and we ask it to do all kinds of different fancy calculations, sure, I can get the computer to give me numbers, But unless I have used the correct test for the variable type and given the study design that we've done, it's just going to give me garbage. It'll give me an answer, it'll give me a p-value, but it won't mean what I think it means. So just be really intentional about being aware that in this case, we have a 2x2 table. That means that we have two dichotomous variables. The exposure is dichotomous and the disease is dichotomous. So those are some important points to remember about arranging the data for this type of study design for rare diseases. Thanks for joining me.